So, now that you guys are sufficiently bored with LiDAR data, we have something new to look at, our face detection. I think I saw that everybody had submitted their project this morning, so that's good. Thank you, Ben, for reminding me I didn't have a Dropbox up there for it. So this is kind of a relevant topic, this face detection thing, now Facebook and all of them have where they'll show where your face is in the image and all that sort of thing. So this is face detection, which is different than facial recognition, where facial recognition is trying to decide who is it or is this that person. So this is an easier problem, just where is there a face, okay? Facial recognition deals with things like how close are the eyes together and things like that, and that's a much trickier problem to say, yeah, it's a face, but it's such and such a person, or it matches the same person as this picture, okay? So originally when I chose this project, it wasn't so much for the face detection, but I was wanting to do something with this technique called AdaBoost, okay? Because it's a popular technique and it's one of the techniques of boosting. And there's other related techniques like bagging and all sorts of, there's different ways of combining classifiers, okay? In this problem, we're going to be talking about a classifier rather than regression. This project's going to be classifying, is it a face or is it not a face? The next project is going to be classifying, is this a cone or is it not a cone? And then after that, then we're going to do regression, where the output is not true or false, but rather some continually varying value. So this is going to be a classification task. And like I said, I'm going after this idea of boosting, which is under the umbrella of what's called ensemble classifiers, or ensemble. I suppose you can do regression with ensembles, but it's more common for classifiers. But an ensemble is where you have, like an ensemble, singing ensemble, where you have more than one person singing. Okay? An ensemble is where you have more than one classifier classifying, and you combine them in some way. You combine these classifiers in some way, okay? So one simple ensemble is, say you have 10 different classifiers, and you ask each of the 10 classifiers, is this a face or is it not a face? And each classifier gives thumbs up or thumbs down. And then you could do, for example, a majority vote, okay? Are more than five or more than 5 of those 10 classifiers saying that it is a face? Well, then we'll say it is a face. And the idea is that if you build your classifiers in a proper way, that you will be more accurate having 10 different classifiers rather than just one. And you'll have 10 different eyes looking at you, 10 different people looking at the same image. You're more likely to get a better result. Okay, so that's the idea behind ensembles in general. You have multiple classifiers combined somehow. Okay, and boosting is one method of doing ensembles, and AdaBoost is one particular type of boosting algorithm, and there's a gazillion of them. Okay, so they're out there, they're pretty common, there's things that you see, and interestingly enough, I'd never really implemented a boosting algorithm. So part of it was too, I wanted to try one, see what it was like, and so I had to learn through this process to be able to do this as well. So it was interesting for me. Okay. So for this facial detection, we're going to be basing it on a research paper, okay? And it's a research paper that was in a conference of computer vision and pattern recognition way back in ancient times of 2001, okay? I mean, that is ancient times in terms of computer vision and machine learning. A lot has changed since then, but this is still interesting. Okay, these types of techniques are still used. If perhaps maybe this one is not, I don't know, if you search face recognition, OpenCV, there's, you find they refer to this article and they, sketch out having to do this type of thing. So it's still even out there, okay? And what these authors were struggling with in 2001 was the speed of the facial recognition. And you'll find that even that's going to be an issue for us too. When we do the cone recognition and the sliding window search, it actually takes a fair amount of time. And one of the requirements on the next, or is it on this one maybe? I can't remember if it's on this project or if it's the next project. But I limit the amount of time that it can run. That for a minute. I think it's the other one. But, we'll find that making the algorithms go fast is an issue, okay? And so what they were interested in here was trying to make this a very high accuracy classifier and be fast, okay? And so they come up with several different techniques for making it fast. One of them is this idea of the integral image that we'll talk about. Another is using this decision tree classifier. That's the cascaded part, where they'll cascade together many classifiers in this decision tree. So there's a lot of what's going on in this article is how to make image face detection faster. Okay. Now, what's really fascinating, I find, with this paper and this approach using the boosting, is that they use what's called weak classifiers, and they boost together weak classifiers and get what's called a strong classification, where the strong classification means it's good. It's a good, strong classification, something you would actually use and rely on. Where the weak classifiers, oddly enough, they only need to be right slightly more than by chance. And if you have enough slightly better than chance classifiers and you boost them together, you can get a very strong classifier. Okay, so of course this is an area of research too where they're proving things like this, that you can get an arbitrary level of classification rates if you have infinitely many weak classifiers that are better than chance. Okay, so of course you can prove all these things and whatever. We're more interested in actually implementing things and doing it, but of course that stuff is out there too. So the idea behind these weak classifiers is really simple, is they're looking at several different types of features. Let's see, they have them here. So they're looking at this type of feature, and these are the same one, but just sort of rotated. This one's vertically oriented, that one's horizontally located. This one is this is basically an edge detector, because what you do is you identify a rectangle part of the image. This here is the whole image, and then this is the location in the image that you're calculating the feature with. And any pixel values that fall under the white area, you sum them together. And then any pixel values falling in the black shaded area, you sum them together, but you subtract black from white. Okay, so if you have lots of strong pixel values in the white area and you have not very much strong ones in the black area, okay, there's going to be a big difference there. And basically this is a way of detecting edges, that there's an edge under there, that there's a strong value here and there's a weak value there. Okay, and so this would detect a vertical edge on that place. This would detect a horizontal edge in that place. Okay, this one they call a line feature, where you have something, basically you have something weak in the middle and something strong on both sides. So you have strong pixel values on the sides, weak pixel values in the middle. And so that would be detecting a line in the middle. Okay, and then this is sort of like a checkerboard pattern. I don't know, they don't really give a good name for that one, so I just call it a checkerboard. Okay, so the idea is we're going to have these different, what are called rectangle features, where the white area represents positive. You add all of the pixel values in the area, and then the black area you subtract all the pixel values to get the feature value. Okay, so this feature only tells you information about what is underneath this part of the image. Okay, so one of the things that they showed here is they look at this image here, that if there's dark things here and light things there, that's likely going to be a face, because in general the eyes are going to be darker than the cheeks in general. Okay? And then this one here is the idea that the eyes are going to be darker than the bridge of the nose. Okay? And so these two features, these authors have found this horizontal feature here at this location in the image is useful, and this line feature here at that location in the image. Those are the two most useful features that they have. I don't know, maybe they have 62% correct rate or something, better than just 51%. Okay? And so they found those are the two best ones. And essentially what we are looking at here is an enormous number of features, because you can have this one here. You can shift it 1 pixel to the right. You can shift it 1 pixel down. You can make it 1 pixel wider. You can make it 1 pixel taller. You can, put that thing all over the place in different sizes, in different shapes. You can have it oriented horizontally. You can have it oriented vertically. Okay? So there's a gazillion features. In this paper, they looked at images that were 24 pixels by 24 pixels, and they said that they had 180,000 different features of all the different combinations of how big those rectangle features were, where those rectangle features were, and whether it was an edge, a line, or a checkerboard feature, and which orientation it was. So there's hundreds of thousands of these features depending on the size of your image. Okay? I have selected to use an image database that's freely available. There's a link in the project description, and it's built on 19 by 19 images. Okay, which is kind of amazing that you can do face detection on only 19 by 19 pixels. One of the senior design teams came to me. They're working on a project where they've got a mobile robot and they're taking a picture of a scene, and they need to navigate through this scene. And there's different objects that they need to detect and get the robot to avoid these objects. And they had they had dropped the resolution of the image down to like 640 by 480 and like a VGA size, which even that is totally unnecessary. I mean, bring it down to 300 by 200 or something. You don't need all of that resolution. The march has been, you guys probably don't remember when the first digital cameras came out, and you had 1 megapixel, and wow, that was awesome. And now, I don't know, what's the iPhone 7 have? 15 megapixels? I don't know. But it's, you have higher and higher resolution. That's what we're used to. We want bigger and better resolution. But a lot of times, that just makes things slow. And it's not necessary. If the features you're looking for are not, don't need that much resolution, here, in this image here, you can see it's kind of pixelated. That's only 24 by 24 pixels. Okay? And we're even using less that's 19 by 19. All right? So, I appreciate that this article is pretty beefy, and it has a lot of details in it, and the notation is really weird. If you're not used to the mathematical notation, that's going to take some getting used to. So what I've done is I tried in the project description to take each of the pieces and describe the things, write the equations, say what the different symbols, what the subscripts and all of that mean, and of course we'll spend more time in class going over these things. I've also built 2 template files for you, okay? One that are sort of helper files that do like the classifiers and the features and that sort of thing, and then another file that actually, is the training process, okay? So I've built sort of a skeleton for you, okay? And of course, like anything, you can follow it, you can not follow it. Will for the last project, you did some sort of collision detection that was different than what I did, right? And Brian came up with a really cool way of not even using collision detection to determine what is the optimum number of classes. It was a really cool technique. So you guys satisfied the spirit of what I was asking for rather than the details, and that's fine. So you're welcome to use this code. If you want to throw it out and write everything from scratch for yourself, you're welcome to do however you want, as long as you satisfy the requirements in the rubrics. Okay? But I think it's probably a good place to start. Okay? So the classifiers.py file, okay? This is the, well, before I talk about that, let's talk about this integral image. Okay. So we need to calculate sums of values under certain areas and subtract sums of values under certain portions of the image. And like I said, this author was really worried about calculating these things quickly. Okay? And so, you know, if you have this feature here and you shift it 2 pixels to the right, you know, there's information in one that you can use to calculate the other. Okay? And I don't know if they came up with this idea of the integral image, or if it was their idea, or if they're just reporting it, but it's quite amazing because it allows you to take the original image and to create a new image, okay, called the integral image. It has the same resolution, so you have an original 19 by 19, and these are grayscale images, by the way. Okay, and so each of these 19 times 19 pixels has a value between 0 and 255. Okay, and the integral image will have the same size. It'll be 19 by 19, but the value in there is not the value, the strength, the gray strength of that pixel, but rather it's the sum of all the pixel values for every pixel from the upper left-hand corner to that pixel. Okay, so if this is our image here, the value at point 1 is the sum of all the pixels in the A region. Okay, and the value at point 4 here is the sum of all of the pixels in all 4, A, B, C, and D. Okay. And what they have shown here is that if, for example, you want the sum of the pixels in the D area, okay, you take all of these. You take if you want what's in the D area, you can add what is at 4, and add what is at 1, and subtract what is at 2 and 3, because 3 is going to be all of this stuff. Okay, 3 is going to be all of that stuff. 2 is going to be all of this stuff. And that encompasses B and C once and A twice. Okay, and so if we subtract 3 and 2, we're subtracting out 2 A's and we're subtracting out B and C. So I need to have 2 A's and then all of the other stuff once. So D is everything once. 4 is everything once. 1 is just A. And then if I subtract 3 and 2, then I get rid of the 2 A's that are there and get rid of the B and the C, and all that's left is D. Okay? So if I have the integral image calculating the value in this rectangle, all I have to do is 4 arithmetic things. 2 additions and 2 subtractions, rather than adding all of the pixels in that region. However many pixels are in that region, I have that many arithmetic operations. Instead, I only need 4 arithmetic operations. Okay? So by having this integral image, it saves me time in calculating these feature values. And if I need thousands of these feature values, it will pay off in the end. Okay, I think their classifier that they used in the end had something like 2,000 features in it. Of those 180,000 total, they had 2,000 of them were part of their classifier. They had an ensemble of 2,000 features. So they needed to calculate 2,000 features, and with this integral image, it'll go faster. Okay? So the first thing you're going to need to do is to take an image and calculate the integral image for it. Okay? And it's really straightforward. I mean, for every point, you need to sum all the things in the top left. I mean, so you could have a nested for loop that goes through all the points, and then inside that nested for loop have another nested for loop that goes through all the region in the upper right corner to add for that piece. Okay? That's actually not as efficient as it could be, and they have a little equation here to calculate the integral image. Okay, so II stands for the integral image, and it's going to have 19 rows and 19 columns. Okay, and XY represent the horizontal and vertical positions of there. So X and Y are going to vary between 0 and 18 for the 19 different positions. And we need to sum this thing little I over X prime and Y prime, where X prime is less than or equal to X and Y prime is less than or equal to Y. And so this other thing I then is defined here. Okay, so where II is the integral image, I is the original image. Okay, so I is the original image, II is the integral image, and so this is the individual. This is the original one. So basically, what this is saying is, in order to get the integral image, I need to sum all of the regular values for all the positions that are less than or equal to the x I'm trying to find. So this equation is a fancy way of saying, to get the value at point 1, I need to sum all the things above and to the left. So in words, I can say it's everything above and to the left. This is the mathematical equation that says that. Okay? And so that's one of the things, as you get more mature in mathematics, is to appreciate that you see that's the way we calculate it. Okay? Now, how you actually do that, okay? They define this thing called S. Okay? And S is a value at any given point x and y. So that also has a size of 19 by 19. Okay? And to get the S value, you're going to take the S value at the y minus 1th position and add that to the pixel value at the current position. Now let me check x and y. Which one is row and column? I'm pretty sure y is got to be column. Row. That has to be the vertical position. Above and to the left. They don't say, do they?
Doesn't matter, does it?
Perhaps it doesn't. I think maybe you're right, Will. It doesn't matter.
As long as it's the same in the program.
Right. So basically, you're going to start at the top left corner, okay? And its S value for y minus 1, that doesn't exist because it's off of the image. So that's basically 0 here, and I just simply add the I value for that pixel. Okay? And that gives you S at that position. Then, in order to get the integral image at that position, I take the S at that position that I just calculated, and I add to it the integral image value to the left of there. Okay, if we're talking X being horizontal position. Now, of course, to the left of that position, there's nothing there, so that's 0. So the integral image for the top left corner is that's going to be 0, so it's just going to be the S. That's going to be 0 because there's nothing above that position, and so it's just going to be the I. So the integral image for the top left corner is just going to be the pixel value of the top left corner. Okay? Then, if I want to go to the next one over to the right, okay? So I'm going to go the next one over to the right. I need to take the integral image just to its left that we just calculated, and I need to get the S value at that position. How do I get the S value at that position? Well, I'm 1 pixel over. I need to look at what is the S above there. That's nothing. And what is the I there? That's the pixel value there. Okay, so the S at that pixel 1 over is going to be the I at that position 1 over. Okay, and so then the pixel value at the position, the first position over, is going to be the sum of the first 2 pixel values. And we can see that makes sense. Okay, and so as I go over from left to right, I keep adding one more pixel, because looking above me always gives me nothing. Okay? And so, you can see, you can work it out. It's going to give you the right thing. Once you're down 1 pixel down, you're going to be looking, what was the value above me? That'll tell me all the stuff that happened above, and I'm going to be adding that to whatever's on the left. And eventually, if you follow this procedure, you're going to get the right answer. So essentially, all you need you're going to have an S matrix. You're going to have an II matrix that is the same size as your original I. And you're going to do a nested for loop through all the positions of the XY, and at every point you're going to be able to define what is the S value there using the top equation. Okay? And then you're going to use that S value that you just stored there to get the II value there using the previous II value and that S value. And then you're going to move over a pixel and you do the same thing, move over, and you're going to keep adding a value into S, keep adding a value into II. Now in the end you don't need S, it's just sort of a help. It sort of stores information you need as you go across the II stuff. Okay? So that's one function that you're going to need to complete. I call it get integral image. So you pass to it the I, and it's going to return the II. All right? Now, so I've described a little bit about that. I've gone ahead in this template file, and it's down there. I put it down there in its complete form, but I'm not going to scroll down there, okay, because you guys need to fill that in. What I want to talk about is how to create the features, okay, because this is what you have in the template file for calculating an edge feature, okay? And so this edge feature takes in the integral image. It takes in whether it's a vertical edge or whether it's a horizontal edge feature. And that's the difference between this is a vertical edge feature, that's a horizontal edge feature. Okay? So this one, I'm breaking my rectangle into left and right halves. So if isvert is true, that's a Boolean. If isvert is true, I'm going to break it into its left and right halves. If isvert is false, I'm going to break it into its top and bottom halves. And I haven't implemented that. That's something you can finish. Okay? So what I have done is, if I am looking at the left and right halves, that it's a vertical edge feature, okay, I'm passing into it the row position of the upper left corner of this rectangle, the column position of the upper left corner, what is the width of this rectangle in pixels, and what is the height of this rectangle in pixels. Okay? Now, if this is a vertical edge feature, the width has to be even, so that there's an even number of pixels on the left and the right. Okay? So, the other thing it also can take in, this is an optional parameter. You can see I give it a default value of none. It's an optional parameter of the original image. And I'm taking in the original image because I'm going to draw on the image to show where this feature is so that we can understand what's going on. Okay? So let me move this over so I can see the paper at the same time. Okay. So what I'm following in here is this approach here, where to get the D, okay, to get the D, I need to take the value at 4, the value at 1, and subtract the values at 2 and 3. This is kind of weird, the notation here, because this isn't 4 plus 1 minus 2 plus 3. It's the value of the integral image at position 4, the value of the integral image at position 1, at position 2, at position 3. Okay? So I need the value of the integral image at position 1, 2, 3, and 4. Okay? And you'll remember here that the integral image gives you the sum of all the values in this region. And what we want is this vertical edge feature where half of the width is the white part, the other half of the width is the black part. Okay, so I'm going to take this rectangle where the upper left corner is defined and its width and height are defined, and I'm going to split it in half down the middle. So the left half is going to be the white part, the right half is going to be the black part. Okay, so I'm defining one 2, 3, and 4 as being the upper left corner, the bottom left corner, halfway across at the top, halfway across at the bottom. That's going to be the left part of this rectangle, the white part of this rectangle. Okay? So 1 is going to be the value of the integral image at the upper left, upper right. Okay? Then 2 is going to be at the upper portion and halfway across in columns. So start at where the upper left column is and add half of the width. Okay? I had problems. Even though I had w as being an integer, when I divided by 2, I was getting a float, and this needed to be a even though w is supposed to be even when it was even, I was getting a float as a result, and so I forced it to be an integer. Depending on how you set up your data types, you may not need that integer there, but I was having problems because even though this divided evenly, I was getting it to be like 4.0, and it didn't like that as an index position, so I put the int on there to force it to be an integer. Okay, so this is position 2 at the top, halfway across the width. Okay, position 3 is all the way at the bottom and at the left side. Okay, so this is the upper left corner. I'm adding the height because 0, 0 is in the top left. Okay, that's 0, 0. Rows get bigger down, columns get bigger to the right. So I'm adding the height to move down to 0.3. So I take the upper left corner, I go down the height, and stay at the same column position. Then 0.4 is going to be at that same row position, the upper left plus h, and move over half of the column distance. So I've now defined 1, 2, 3, 4 for the left half of this rectangle. And so the d value for the left side is 4 plus 1 minus 2 plus 3, quantity 2 plus 3, this equation right here. So that gives me the sum of all the pixels in the white left half of this rectangle. Then I need to do the same thing for the right half of the rectangle. Okay? So, now this is a little tricky. I need to now make 0.1 needs to be where 2 was before, because I need to shift over. So I could just define them over again. Maybe that would be easier to say. But basically, I want this to be 0.1, that to be 0.3, 0.2 to be the other half of the way over, and 0.4 to be the other half of the way over. So I'm going to make 0.1, this be 0.1. So what used to be 0.2 is now going to be 0.1. What used to be 0.4 is now going to be 0.3. And then points 2 and 4 need to be on the far right of the rectangle. And that's going to be when I add all of the widths to the column, either at the top or at the bottom. Okay, so now 1, 2, 3, 4 are the right half of this rectangle, the black half of the rectangle. So then the feature value, and then I'm going to take 4 plus 1 minus the quantity of 2 plus 3 to get me the d value for the right half, the black half of this feature. And then the result is I'm going to take the left half and I'm going to subtract the right half. The left half is the white, that's positive. The right half is the black. I'm going to subtract. Okay? Now, if something is passed for image, if image is not the default none, if I do actually pass the original image, and I don't know, maybe I should have called that I instead of IM. If you go into like Matplotlib and OpenCV, they use as the default variable for image, they use the term IM. So for image, IM. But in the paper, they use I to represent the image. Okay, so I used IM here. Perhaps I should have made it I to be more consistent with the paper. Okay, so IM is the original image, and what I did here is I went ahead and I set. I don't know. Move over. Don't want to move over for me? Fine. What I did is I set the left half of the image, okay? So from the top to the bottom, from the left to halfway over, to be white. And then I set from the top to the bottom, from halfway over to that's halfway over to all the way to the right, make that black. So basically whatever the pixel values were there before, I'm drawing the feature thing on top of it, the black and the white thing. Basically I'm trying to create sort of this image where I'm overlaying the feature's position on top of the person's face so that I can see where this feature is and where the white and the black stuff is. Okay? Now, you'll notice I never returned IM, did I? I only returned the feature value. Okay? And this makes use of a very curious and significant difference between Python and any other language I've ever seen. And that is that when you create a variable and you say x equals 5 and then you say y equals x, in another programming language it would take the value in x, that 5, well, first it would allocate new memory for y, and it would take the value that was stored in x and copy that over to the memory position for y. And x and y would be in different memory locations but have copies of the same value. That's the way you're used to it working when you say y equals x. That's not what Python does. Okay? When you say x equals 5, it says, okay, I need a memory location for x, and I'm going to store 5 there. Then when you say y equals x, what it says, I'm going to make y a pointer to point to the same place that x is. So they share the same memory position. And if you change either x or y, both of them will change. Okay? Which is really curious. Okay? So it's really weird. So if you set y equals x, you have one copy and they're both pointing to the same places. And if you change one, you change the other. And one of the indirect results of that is that when you pass something, you're copying the old parameter in the global workspace and you're passing that to this function. You're saying the local variable is equal to the global variable, which means they're going to share the same memory positions. And if you update it inside the function, it will be updated in the global space. So essentially, everything in Python is passed by reference. Everything is passed by reference. So if you change something inside the function, it will change where it was called from. Okay? That bit me many times before I really understood that. Okay? So be careful of that. So it's nice that here I can change change the image here in the function. I don't need to return it because it's passed by reference. But I need to be careful because if I didn't want it to be changed, I just did. Okay? And that's why doing copies and deep copies, if you want to be really careful, because there's all sorts of idiosyncrasies with copying over lists. If you want to make sure that when you want to set y equal to x and it be a new thing, do a deep copy of it, and then you'll be sure that it'll be by itself. So here I'm changing the image, but I want that to be changed back in the calling function so I can see where this feature is. Okay? So I've implemented the vertical edge feature here. Okay? You need to implement the horizontal edge features. Okay? This part down here. You also are going to need to create a line feature. Okay? You'll want to create a line feature. That's this one here with the 3 parts. Okay? And even a checkerboard one. Okay? That'll give you even better classification results if you can use all 3 of these types, an edge, a line, and a checkerboard. Okay? And have all of your combinations of them. Okay, so let's use this edge feature. And so you notice I have this classifiers.py file, and then I have this testcode.py file, and these 2 files are in the same directory. Yes?
So back on the classifiers, we were talking about linking the horizontal one.
Yes.
We're essentially taking the top from the vertical one and then changing the row and the columns to match up like.
Right.
But would we still want to keep like the positions 1, 2, 3, and 4 the same, or do we want to do it 1, 2, 3, and 4?
It doesn't matter as long as you're consistent. If you change where 1, 2, 3, and 4 are, you're going to need to change the equation for D.
Got it. Okay.
So my recommendation is that you leave 1, 2, 3, 4 in the same position relative to each other so that you can use the same equation, but it doesn't really matter. Basically, instead of going from the row all the way down and having the column go halfway across, you're going to have the rows go halfway down and the columns go all the way across. So basically you just sort of need to do like a transpose almost on it. So you can basically copy and paste that into and sort of change things around so that it's doing the top half and bottom half rather than left side and right side.
Is there a good way to test this?
Yes, and that's the idea. That's why I did this visualization part, because I wanted to be sure that because and you'll notice that this stuff here mirrors what's going on here. I'm going from the row all the way down the rows, and I'm going from the beginning to halfway across to the far right, just like I'm going, so these things mirror that, and that's how I wanted to confirm for me that it was right, that when I drew it with the same index positions, that it drew what I wanted. So that was the way I confirmed it.
So just by having IM be true, it does draw it?
So if IM is anything other than none, don't you love this? Don't you love that syntax? If IM is not none, you gotta love it. Okay, so if you pass something in for IM that's not none, then that if statement will trigger. Okay, so as long as it's not none, it will do it.
So IM equal turkey works.
Yeah, I mean it will give you an error if it's not the right size matrix or something, but yeah, if it's anything other than none, if it's a string, it'll do that if statement. Whatever. None is a really curious animal in Python. It's kind of neat. So classifiers.py is a Python file, and this is really cool that I've created my own module in that classifiers.py file, and I can import that. And so that any of the functions inside the classifiers.py, such as feet edge, I can access with classifiers.feetEdge, just like when you import matplotlib. Okay? Now, I've had trouble on my computer. Sometimes it works, and sometimes it says there is no such module called classifiers, and I'm not sure why. It works sometimes, and it sometimes doesn't work. This case, it is working for me. Okay? If you get into trouble where it's not working, it won't let you import the classifiers, it'd be awesome if you could help me figure out why it works sometimes doesn't. But if you're tired and don't want to do that research, you can just copy and paste your stuff and put it in up here in the top. Okay? The reason that I put it in its own file is because you're going to create two files for this project. You're going to create a file to train it, and you're going to create a file to evaluate it. And so both of those files are going to need the stuff that's in classifiers, and it's nice to have one copy in classifiers.py and import it in both places rather than having two copies that if you change one, you need to remember to go change the other. So it's convenient if you're able to make it import classifiers. I'm just not savvy enough in Python to know why it's worked for me sometimes and not others. Okay? All right. So I'm also using this interesting module called glob. Okay, and the glob thing allows you to glob together all of the files in a directory. So basically, once you import glob, there's a command inside glob. So if you glob and you give it a folder and even a wildcard for some type of a file name, okay, what files will return for you? Let me run this. What files, and I did a print on files, and basically it prints here all of the file names in that directory. Let's get it there. That's a nice one. So basically now files is a list. You know what? Let me do a reset here. Run it again. So files is a list. There's 2,000 elements in the list, and each element in the list is a string with the file name for each one of these files. So these are all of the files that you download. There's 1,000 training files, and I guess there's 1,000 for training and 1,000 for now I'm trying to, I want to remember, did I make that where you download them yourselves, or did I upload them for you? Pretty sure. Okay, so I created the file for you. Okay, so I got them. So I got them from this MIT website. So I didn't give you the URL, but I have a zip file with all of them in there. Okay, so inside the zip file, here's that zip file. Inside of there is a folder faces, and then inside are test and train. Okay? So once you unzip it, you'll have this faces folder with the test and train folders in there. Obviously, the ones inside the train folder are the ones you're supposed to use to train it, and that's obviously for testing. Okay? And there's a folder for faces and for non-faces. And apparently there's 1,000 faces, or there's 1,000 in here, or there's 2,000 faces in the training set. Okay, so this is starting to get lots of data. There's 2,000 faces in the training set. Let's see how many non-faces are there. There's 4,000 non-faces in the training set. Okay, so there's lots of files here, and what I asked you to do when you submit this is to not include all the images in your submission. Okay? But rather expect that the faces folder exists in the same folder where your submission is. Because you're going to have a folder and zip that whole folder, and everything in there is your submission. The faces folder should be in the same location that your folder is. And that's why in this file I do .. That says go back one folder. And then go into the faces, go into the training, go into things that are faces, and get all of the .pgm. That's a image format that I'd never seen before. Me neither, but for whatever reason they use it, and you can load them. All the software will load them in fine. Okay, so you load in. So it'll load in. This gives you a list with all of the 2,000 file names, and you could do a for loop to loop through each one of those and load in file 0, file 1, file 2, file 3, all the way up to 1,999. Okay, I haven't written a for loop to do that, but rather I printed all the files. You can see there's all of them. Then I printed what is the file name of the first one. That's this one here. And then I'm going to go ahead and read it using matplotlib's imread. Okay, now it's a little bit of your preference. Do you use OpenCV's stuff, or do you use matplotlib's stuff for doing images? I personally like plotting stuff in matplotlib because it's closer to MATLAB and I'm used to that. And plotting things and stuff in OpenCV is a little bit different, and I don't like it as much. Okay. One thing to keep in mind: if you load an image in matplotlib, it is RGB. If you load a color image in OpenCV, it's BGR. So if you load something in OpenCV and plot it in Matplotlib, it'll look weird because the red and the blue are switched. So beware of that. These are grayscale, so you don't have to worry about it. Okay? I don't know. So here I'm getting all the files. I'm actually only going to read in the very first one, but you could loop through all of them. Okay? Then I'm going to open figure 1, clear it. I'm going to do an IM show with plot of the image. I'm going to tell it it's a grayscale. I want to use the color map for gray. Then I'm going to calculate the integral image, which you guys haven't implemented yet, but I have done. And then I'm going to do an edge feature, where I'm going to pass the integral image, and I know we're just about done, but let me wrap up here. It's going to be true, that is vertical. Right now, the horizontal one's not implemented, so it wouldn't work if I did faults there. I'm going to have the upper left-hand corner be at pixel 6, 6. It's going to be 4 pixels wide, 8 pixels tall, and the IM variable inside the inside the function is going to be the same as the IM variable here that I loaded in. And so when I run that, I get figure 1 looking like this. And then after I plot figure 2, so once I call edge feature, it changes IM. So if I do IM again, it has the white and the black. Okay, it's at pixel 6,6. See 5, 5, 6,6. That's the upper left corner. It's 1, 2, 3, 4 pixels wide. 2 of it on the left half, 2 of it on the right half. And so then I can change that. I can say, well, let's be at 10, and let's make it be 12 pixels wide. So now I have 12 pixels wide, 8 tall, and it's starting at 10.6. So this is how I visualize, how I've confirmed for myself that I'm pretty comfortable that this feature works right. Okay? And I didn't print the actual feature value. I should print F. What is the value of F? Here's the feature value. It's negative 420. So apparently there's stronger pixels in the black part than there are in the white part because it's negative. Okay? And then you can mess around with this. Maybe I'll upload. If I can remember, I'll upload this to D12 too. But at least when I do the recording, you've got that there. Okay. So let me go ahead and stop there. Move on and we'll do some fun AdaBoosting. It's really cool.